Hi, I'm Ruth Ashbee. Welcome to my CogSciSci Soapbox on language and ideas in radioactivity. I'm a bit worried about radioactivity. I feel like it's such a wonderful topic. It's so fascinating. It's got that kind of wonderful cross between the observable and the unobservable. It takes students into fantastic parts of our understanding in physics. It's got that kind of counterintuitive and surprising aspect that makes physics so exciting. And the reason I'm worried about it is I don't think that we are often as precise with our language as we ought to be. I feel that as specialists, there is a wealth of understanding about radioactivity that sits behind a lot of the language that we use, and that we make quite a lot of assumptions about knowledge in the use of that language sometimes. I worry that not all of those assumptions are always clear to our students and that we need to make them clear. And I worry about some misconceptions that can start to build because of any sort of grey areas that might arise from the way that we use language. So I'd like to go through some of the things that I think we should be thinking about, and then I'll propose a few solutions that we might begin to look at going forwards. So the first thing I think that can be problematic is this word radiation. Now, whichever order you teach your curriculum in, students will encounter this word in two separate topics. In the radioactivity topic, where they'll learn about alpha, beta, gamma, and neutron radiation, and in the waves topic, where they'll certainly learn about electromagnetic radiation, so radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays, and then they might you might term sound as radiation within that sort of topic as well. Now, I've sort of set these out in this diagram here to show that gamma radiation, of course, sits in both of these categories. And I think that it's worth making that very clear to students, because it's quite common to come across students who will dutifully talk about gamma radiation as nuclear radiation and as a high frequency electromagnetic radiation, and not make the connection that it's the same thing. So I think we need to make that really, really clear to students. And it can be a bit confusing why we've got these two separate categories, but there is one type of radiation that sits in both. And it's worth spending a bit of time thinking about that. The category of nuclear radiation is a category that talks about the origin of radiations, whereas the category of electromagnetic radiation is talking about the intrinsic properties of radiation in terms of them being an electromagnetic wave and an oscillation in the electromagnetic field. So that is sort of quite conceptual, but I think that if we're going to bring students into the understanding that we as specialists have, then that's something that we need to be clear about before we begin teaching. One of the things that I think we do naturally as a part of this topic, and I think it's an important and intrinsic part of this topic, is this jumping between scales and levels, and talking sometimes about individual nuclei and individual emissions, and at other times about aggregates of large numbers of nuclei or streams of emissions. And when we make those jumps, misconceptions can arise. If students aren't clear that we're making those jumps, they can get confused very easily and build up a faulty picture of the knowledge in the subject. I think we're actually quite explicit about this jump when we're talking about the links between the random and unpredictable nature of individual nuclear decay, and the fact that when you've got a large number of nuclear decay, of radioactive unstable nuclei, that we can make predictions about the behaviour of large groups of these individually unpredictable things. However, elsewhere, I don't think that we're clear enough at all. So I'd like to look at a few examples of that. Penetration power. This is one of the archetypal diagrams of radioactivity, and it bothers me because I think that there's quite a few misconceptions that can arise from here. We've got an alpha particle here drawn and labelled, a beta particle here drawn and labelled, and well, it says gamma ray, but it looks like we've sort of got three waves being drawn there, and 3 different outcomes when each of those waves encounters the lead material. And indeed, the word ray itself is, I think, fairly ambiguous, and can sometimes cover both individual and groups of waves. The misconception that I'm worried about here, though, is this idea that alpha particle has a binary relationship with paper, in that every alpha particle will always be stopped by paper, and similarly that beta particles will always be stopped by aluminium. And that's just a terribly oversimplified picture, and in that simplification, I think we run the risk of misunderstanding what's really going on, because of course all these emissions come in streams and ranges of energies. Each individual emission will actually be coming out in a range of angles as well. The materials themselves come in ranges of thicknesses. So there is not this binary relationship where a particular type of radiation is automatically going to be blocked by any version of this particular material. This is a graph that I think is quite useful to share with students. It shows that paper is a blocker of beta particles, but that a beta radiation stream is made up of a large number of particles, and that the thicker the paper, the more of those individual particles are stopped, but it's certainly not an all or nothing situation. I think that when we talk about radioactive materials, there's a lot of assumptions in our language that we need to be aware of, and there's a lot of terminology that we use quite freely, I think, often, and it's very easy for students to get overwhelmed with a large amount of new terminology being used kind of all at once. The whole concept of isotopes is absolutely fundamental, isn't it? Not just to kind of understanding what's happening in radioactivity, but the way that we talk about materials and radioactivity is often completely predicated on the concept of isotopes. So we often, having gone through the whole of science, just sort of referring to materials by their chemical names, by the names of their element, for example, if it's an element, we now all of a sudden start putting a number on the end of things. So we've got cobalt-60 and so on. And, that's, as it should be, that's the way that we talk about materials. That's one of the ways we talk about materials in this area of physics, and I don't think that we should change that, but I think that we need to be aware that putting a number on the end of it can suddenly make it look very unfamiliar, and it adds to the cognitive load for our students, and I just think we need to manage that. I think we often talk about stable or unstable isotopes, and we sometimes aren't entirely clear with students whether we're talking about a particular lump or a sample of an isotope. There's another word that we use very freely, but is new for a lot of our students, or a particular nucleus of an isotope, or just the isotope, cobalt-60, as a platonic form, as a thing that exists in some kind of conceptual plane and has kind of general properties. We can flip between those quite easily, I think, and bring confusion for our students. And this word source, I think, can carry a lot of confusion for our students. As specialists, we use it to refer to a material that's giving out radiation of a particular kind, but it's just another word that we're using to describe a material, from the point of view of our students, and that's compounded by the fact that source has got a kind of very everyday meaning, and so it doesn't really look like a sort of scientific word. And that can bring, I think, difficulties for some students. I worry a bit about some of the misconceptions we might introduce as well by the way that we talk about sources. I think we often talk about them as kind of like an unchanging, sort of static material, and that's of course not accurate, because we've got, if it's giving out emissions, then nuclei will be changing to other nuclei in that source. And often we talk about a source of, a particular type of radiation, and of course, usually sources give out more than one type of radiation, and I think that can be kind of almost very contradictory for students. In one lesson, we might talk about how gamma radiation is always the after effect, if you like, of an alpha or a beta decay, And then in another lesson, we'll talk about a gamma source without acknowledging the fact that, of course, there must be either alpha or beta or both emissions coming from that source as well in order for gamma radiation to be being produced. So I just think we need to be really careful and plan really well to make sure that all these holes are sort of tied up, and that all these, that we present a picture that makes sense and doesn't have any of these contradictions for our students. Because if they've got these kind of questions formed or unformed, or these loose ends not tied up in their minds, they're not going to take a secure set of meaning from the curriculum, and they're going to either just not remember it very well, or just develop misconceptions to try and make sense of it all, and neither of those things are what we want. This word decay is another word, isn't it, that's got a very everyday meaning. We talk about tooth decay and decaying fruit and dead bodies and all the rest of it, and we just need to make sure that our students are clear that it's got a very specific name in physics. We talk about nuclear decay, radioactive decay, and then just this kind of overarching term, radioactivity. But all of those terms, I think, can be quite broad, and they're not entirely clear, or I think they're certainly used both to talk about aggregate events or products of lots of nuclei or emissions, and but then sometimes it's used to talk about specifics as well. So I just think we need to be aware of those two types of reference. We can be very specific and use the term decay event, or the decay of a nucleus, or talk about the decay of a nucleus into a daughter nucleus. And those two terms I would advocate trying to use if we are talking about a particular event. I think that that's a good way of bringing some much needed precision to the area. And then here's some more ways that decay is used. We talk about decay curves. That's obviously talking about an aggregate, but that's not it's not obvious to students. We need to make it obvious. We talk about decay over time. Again, that's an aggregate thing we need to be clear on. And then again, you see people talking about decay of an isotope into a daughter isotope. And again, we could be talking about an individual atom there, or a platonic form, or something in between. And we just need to be thinking about which one it is we mean, and how we can get our students to know about which one it is that's meant. What do we even call like the group that is alpha, beta and gamma? I've seen it called radioactive emissions, which I think is problematic, and radioactive particles, which is even worse. Like, that's definitely wrong, isn't it? So I'll put those two things in scare quotes, because they're not what I think we should be using as a collective term. I think nuclear emissions is a useful term to talk about the individual particles or waves as a set. We can talk about nuclear radiation. I think that that's got, I think that tends to be used to talk about a stream, but I don't think that that's intrinsic to the definition of nuclear radiation. And then this term ionizing radiation as well, I mentioned earlier, can be useful. Just bearing in mind, of course, that neutron radiation is excluded then. Lots of students ask me what happens to alpha, beta and gamma in the end. And I think that it's really important. This is often, this isn't really part of the sort of the specified knowledge in the curriculum, like the specification. And I think it sort of needs to be, because our narrative is sort of truncated. It's a bit abortive, isn't it, if we sort of spend all this time talking about alpha and beta and gamma and penetration and all the rest of it, and then we just don't really kind of give the conclusion, which is that after the alpha particle has travelled through a short amount of a small amount of air, and has collided with a particle in the air, it loses lots of its energy. It will pick up some electrons from somewhere and just turn into a normal helium atom, and a similar but obviously importantly different story for beta particles. That's really important, isn't it? And I think that just being able to sort of tie up that loose end, and bringing students into this understanding that all around us there are atoms that have got an electron in them that used to be a beta particle, and helium atoms that have gained electrons where previously they were alpha particles. that's a really powerful connection, I think, to have between sort of school physics lessons and the thinking self and the tangible world around us. And I think that that's a really important part of the story that we should be explicit and plan for and tell our students. If some of our students are asking this question, then you can guarantee that lots more of them are thinking it, or have got it half formed in their minds, or have got a loose end that hasn't yet been dealt with in the understanding that they've got. And I think that we should make sure that their understanding is complete and satisfying in that sense. So the solutions are kind of, not rocket science, but I think it's just about kind of being aware of all of these things, being intentional, thinking about where we're using these terms, what it is that we're actually meaning by them, how we can stagger all the new sort of terminology and give students kind of examples and non-examples and precise definitions of how they're used. The way that we speak and the way that our explanations are written, if we're using booklets, I think has to be absolutely, executed with a really high attention to detail and backed up by a really clear understanding of the physics that lies behind all the use of this language. And one of the things I think is really important is providing practice for students in the use of this language, both in spoken and written work. And one of the things I've noticed is that a lot of the practice questions that one comes across for radioactivity don't have this kind of like, I want to say literacy type question, but like not in an annoying way, in a in a really meaningful kind of developing precision of thought through the precision of language, because there's a lot of language to be used. So that's something that I think that would be a really useful development in terms of resourcing for this area. One of the things that we do in my school is begin to teach some of the concepts of radioactivity. So the types of decay and emissions and the penetration power, for example, in year 7, just so that students can begin to get a sense of, I think when you know about radioactivity, that you can feel how like big and kind of boisterous an alpha particle is, and sort of the kind of ghostly nature of a gamma ray, because you've just been used to thinking about them and their interactions for a long time, and that's something that we want to give students an opportunity to spend time thinking about in Key Stage 3, and for various other reasons we feel it sort of feeds into various other curriculum areas in a powerful and meaningful way. So we've got a short unit for year 7 on radioactivity, for which the booklet I have put on my blog. So please do have a look at that, and if it's any use, then that will be wonderful. One thing we haven't looked at yet is the sorts of things I just mentioned about the written work and practice for students. So that would be a wonderful contribution or area to work on going forward for the CogSciSci team. If you'd like to get involved with CogSciSci, please do tweet or get in touch via the hashtag. And thank you very much.